So with work and energy, we began looking at work, and work is a quantity that describes the displacement of an object times a force parallel to the displacement. So within the work equation, we have the the angle built in here. We have the force. We have the displacement, and yeah, it builds the trig right in there. So a Newton meter is the work that we have there. And again, this is a very particular kind of work, mechanical work, as we look at this. All right, so let's go ahead and apply this. Why don't you go ahead and pause the clip and give this a try. And you can do part 1, 2, and 3 here of this question. And when you're ready to check, you can hit play to continue. All right, so for the first one, we have our force, and we have our displacement. And the force applied is to the right, displacement's to the right. So the angle between the displacement and the force is 0 degrees. And we can apply the force, and it'll go to the right. The second one, the box is lifted into the air. We can do our sum of the forces. So sum of the force of the y, positive force applied plus negative force of gravity, and those are balanced. So 519.4 newtons is the force up, and the displacement is up, the force applied is up, so the angle is 0 degrees, and we have 779.1 joules. And then the last one, box is carried 15 meters, the force applied is up, displacement is to the right, and we want to know how much work is done. So yeah, for this one, this is the classic example where you have a force, you have a displacement, but the angle is 90 degrees. You're actually not doing any work, mechanical work, because the force and displacement are not parallel to each other. All right, so when we calculate kinetic energy, it's energy due to motion, 1/2 mv squared, and v is speed. So energy we get in joules, and it is a scalar. Energy is a scalar quantity. There's no direction with that kinetic energy. Potential energy, energy due to position or configuration, and gravitational potential energy is mgh, mass in kilograms, height in meters, and we use G 9.8 on Earth for the potential energy. And if let's say we had an object on the moon, we'd have a different acceleration due to gravity, and that would just replace G there. All right, so let's go ahead and practice this here. We have a 100 kilogram crate lifted to a height of 12 meters. What's the potential energy of this compared to the same crate that's lifted 24 meters into the air? So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so we have our force applied up, and we can get the energy here of, at that height, 12 meters, and so 11,760 joules, versus the second height, the 24 meters, 23,520 joules. And if you can see here, the energy is double at the second height, and that's what we see there with the energy. The potential energy is directly proportional to the height. All right, so for this one, we've got a 48-gram bullet going 100 meters per second. How does the kinetic energy of this bullet compare to the same bullet going 200 meters per second? So go ahead and pause the clip and do both of those. And remember, with your units here, be careful. And when you've got those, go ahead and figure out how many times greater the second one is compared to the first. So go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. All right, so conversion to kilograms, 0.048 kilograms, and so at 100 meters per second, we get 240 joules, and then at 200 meters per second, 960 joules. So 4 times greater, right? And we see that because speed is has an exponential effect on kinetic energy, and we can see that with the speed squared there, 1/2 mv squared, and v being speed. All right, so let's go ahead and try this one here. We have a mass that's being pulled up at an angle, 125 newtons at 25 degrees, and we want to find the work that's done. So go ahead and pause the clip and give this a try, and when you're ready to check, you can hit play to continue. Okay, so force times displacement times cosine theta. We have our force, we have our displacement. times the angle, so 1,132.88 joules is the work that's done, or Newton meters. And if you notice here, 125 newtons times cosine of 25, that's the adjacent side. So what it did is it got us the adjacent side force and multiplied by the displacement, because remember, work is what's the force and the displacement parallel to each other, and we multiply those, and so it takes care of the trig force in there.